Now, we are going to explain frequency tests where we check the uniformity of our random number sample. And we can use either of the following two tests, Kolmogorov-Smirnov tests and chi-square tests. So both these tests measure the degree of agreement between the empirical distribution of a sample generated from random numbers and the theoretical uniform distribution. There will be an empirical cumulative distribution function that is going to be generated through your sample. Now we need to check the difference between the empirical CDF coming from the sample and the theoretical CDF of the uniform distribution. And if there's a significance difference between these two cumulative distribution functions, then we are going to reject the null hypothesis. Okay, we will say that there's a statistical significant difference between the empirical and the theoretical distributions, then we reject the null hypothesis. Now, for every statistical testing procedure, we need to determine a significance level alpha. And based on the significance level, we are going to check if there is a difference between the theoretical distribution and the empirical distribution. Now, first we are going to use the Kolmogorov-Smirnov test. As we have said, Kolmogorov-Smirnov test is a much stronger test than chi-square test. So it is always better to use Kolmogorov-Smirnov if you have strong computers. The fact that Kolmogorov-Smirnov test is also a better choice is that it can be used for any sample size. I mean, even if your random number sample or random number sequence for testing is of size 5 or 10, okay, even if it's a very small size, you can still use the Kolmogorov-Smirnov test. However, chi-square test is only usable when your random number sequence size or the sample size is greater than 50 at least. So here 50 is basically an arbitrary number given by the literature, but what we want to indicate here is if you want to use the chi-square test to check the uniformity or as a frequency test, the sample size must be large enough. Okay, so that's basically the golden rule here. And chi-square test is not as strong as the Kolmogorov-Smirnov test because it gives away some information about the sample. However, it has less complexity than Kolmogorov-Smirnov test. Therefore, it is going to be much more faster to implement the chi-square test. Okay, so let's start with the Kolmogorov-Smirnov test. So as we have said, the frequency tests are comparing the theoretical distribution and the empirical distribution of the sample. Now, how you can make this comparison? By comparing CDFs, for example. So we have a theoretical uniform CDF, capital Fx, which is the identity function, if you remember, between 0 and 1. It is just a linear function. And the empirical CDF, Sn of x, where you have a random sample of size n. So you have a sequence of random numbers starting from 1 to capital N. And this Sn of x is the empirical CDF, which is defined in this form. And it is a very, very simple definition. So the empirical CDF x means the number of random numbers in the sequence which are less than or equal to x divided by the total number of random numbers. So Sn of x is the ratio of the random numbers that are less than or equal to x in the whole sample. Okay, so that is as simple as it goes. And of course, as x here increases from 0 to 1, as we move to the right hand side, every time a new random number is going to be less than or equal to x if you increase x. And therefore, this ratio is going to increase as a stair-shaped function starting from 0 to 1. Okay. Now, there will be a linear function directly connecting from 0, 0 point to 1, 1 point, a linear function, identity function, and there will be a stair-shaped function increasing in the form of a staircase, and we are just going to check the difference between these two functions. All right, so here's our first example. It says, consider the following random number sequence. This is my original sequence that consists of 5 random numbers. And of course, they have a low resolution because, I mean, this is just a small size example and we want the students to understand the calculations here. Now, let's just say we have sorted these random numbers from smallest to largest. Okay, so they are sorted in a non-decreasing order. And you see in this picture, for these sorted random numbers you see above. In this sequence, you see the red line as the theoretical CDF from 0 to 1 on the x-axis and on the cumulative probability axis again 0 to 1. And we have an identity function that is the theoretical CDF. Now, what is the empirical CDF? Remember, it is basically calculating the ratio of numbers in our sample which are less than or equal to x. Okay, proportion of the random numbers which are less than or equal to x. For example, at 0.5, what is the empirical CDF? Now check how many random numbers here are equal to 0.5? 3 of them. Therefore, the empirical CDF must be equal to 3 over 5. Now, how can you draw the empirical CDF in the easiest manner? You can start from 0 here, and you can move constantly. When you reach to your first observation in the sorted sequence, in the ordered sequence, you jump to 1 over 5. Why 1 over 5? Because there are 5 observations. So you basically have a jump of size 1 over capital N. Then you move again. When you reach to 0.14, you make another jump to 2 over N. When you come to the third observation, you move to 3 over N, 4 over N in the fourth observation, and 5 over N in the fifth observation, and it goes like this. But since we have 5 observations here, at 5 over N, we reach to 1. So basically, in the projection over the x-axis, you are going to see the observations here. Now, I am just going to check the maximum difference between the theoretical CDF, which is a linear line, and the empirical CDF, which is a stair-shaped function. And the maximum difference is observed at here as 0.26. So the maximum distance from the theoretical CDF to the empirical CDF is 0.26, as you can see it here. Now, of course, if we are going to make a conclusion about the uniformity property, we need to compare this difference 0.26 with a critical value. And after this comparison, if this maximum difference is assumed to be significant, then we reject the null hypothesis and we will say that this sample is not uniformly distributed. But you see, if really the sample is uniformly distributed, this stair-shaped function is just going to oscillate with small magnitude around the theoretical CDF. All right. So in this example, we have the original sequence of 8 numbers this time. And we have the sorted version of these from smallest to largest. And again, you see, we have the theoretical CDF, which is a red line. And this is our empirical CDF, which has a stair shape, but this time it consists of 8 steps. So your first jump, starting from 0, your first jump is observed at 0.045 as 1 over 8, size 1 over 8, or 0.125. Second jump is observed at 0.287. The third jump is just observed after 0.408. So you are at 3 over 8 here. You come to 4 over 8 at 0.528. And you see there is a long run here. And after this run, at 0.788, you jump to 5 over 6, 8, 6 over 8, 7 over 8, and 1. So you see, again, we have the empirical CDF. This time, the maximum deviation is, I think, observed around here or maybe here. Okay, most probably it is around here, but it may also be here as well. So by looking at the figure, the value where we observe the maximum deviation between the both CDFs, the maximum deviation, is not easy to determine by looking at this picture. So we need to develop a methodology, an algorithm to identify this maximum deviation. Now, this is the algorithm of the Kolmogorov-Smirnov test. And what we are going to do in the first step of the algorithm, first we are going to rank the sample from smallest observation to the largest. So we are just going to develop the order statistics of this random number from smallest of the observations to the largest. So these R parenthesis 1 means the smallest observation. R parenthesis I means it is the ith observation in the order sequence. From smallest to largest, it is the ith observation in the order sequence. So if it was just writing Ri without any parentheses, this means this is my ith observation. However, if it writes R parenthesis I, this means it is the ith observation in the ordered sequence. Now, I'm just going to calculate I over n minus Ri values for each I, starting from 1 to n, and I will find the maximum of these values, and I will call it d plus. And then I will calculate Ri minus I minus 1 over n values for each I value here from 1 to n, and I will calculate the maximum of them, and I will call that d minus. And then I'm just going to compare d plus and d minus, and the maximum of these two values will be called d, and that is my test statistic, which is the maximum deviation between the theoretical CDF and the empirical CDF. Then I'm going to compare this d value with a critical d alpha value in Kolmogorov-Smirnov critical values table. And of course, we need to identify a critical d alpha value for a specified sample size capital N and for a specified significance level alpha. And then if the maximum absolute difference between both CDFs, D, is greater than this critical value, in that case, this difference would be assumed as a significant difference, and we reject the null hypothesis and say that there is enough evidence to say that the sample does not follow the uniform distribution. And otherwise, if this deviation is less than or equal to d alpha, the critical level, then we say that there is not enough statistical evidence to reject the null hypothesis. The random number sample may fairly come from a standard uniform distribution. Now, this is my Kolmogorov-Smirnov critical values table, which is taken from the last pages of your textbook. And you see, we have the degrees of freedom here, which is the sample size in this case. So the sample size, capital N, is here. And for alpha values, for significance levels 0.10, 0.05, and 0.01, we have the critical D values. When your sample size in a Kolmogorov-Smirnov test is greater than 35, then you can directly determine your critical value using these formulas. All right, so we are just going to apply the Kolmogorov-Smirnov test to the first sample in the example that we have shown. So let me go back a few slides back. Remember, the maximum difference between the theoretical CDF and the empirical CDF was 0.26, and we would like to identify that maximum difference. Instead of drawing a plot diagram, we are going to use the algorithm this time. And the algorithm is performed through this table. First, we write down our random numbers, and in the next column, we write down in an increasing sequence from smallest to largest. So you see the difference between, this is the random numbers in the observation order, and these are the random numbers in an increasing order. Now, I am going to calculate I over n here, and I over n will be 1 over 5, 2 over 5, 3 over 5, 4 over 5, and 5 over 5 for each index here. And in order to calculate the d plus value for each row here, I will calculate I over n minus Ri. So 0.2 minus 0.05 is 0.15, 0.4 minus 0.14 is 0.26, 0.6 minus 0.44 is 0.16, 0.8 minus 0.81 is negative 0.01, and 1 minus 0.93 is 0.07. Then we also calculate our I minus 1 over n. But this time, you need to subtract 0 from 0.05, 0.2 from 0.14, which makes minus 0.06. You subtract 0.4 from 0.44, it makes 0.04. 0.6 is subtracted from 81.81, it makes 0.21. And 0.8 is subtracted from 0.93, 0.13. So the long story short, you are basically comparing each random number in the order sequence from the theoretical upper bound and the theoretical lower bound So the distance to theoretical upper bound is 0.07 and the distance to theoretical lower bound is 0.13. So the distance of 0.81 to theoretical upper bound is negative 0.01 and to the theoretical lower bound is 0.21. So basically we are doing this. And then for each column here, you are calculating the maximum of these differences. So in this column, the maximum is 0.26 and in the next column, the maximum is 0.21. Please note that you are not calculating the absolute values here. You are just calculating these differences, not absolute values. And then when you are calculating the maximum of them, again, negative values are going to be assumed as smaller than the greater value. So you are going to find the maximum positive value here. And then we have D26 and D minus 0.21. The maximum of these two values is 0.26 is the maximum deviation of your theoretical CDF from the empirical CDF. This is my test statistic. Now I am going to go back to Kolmogorov-Smirnov table for a significance level of 0.05 and sample size of 5. Now for significance level of 0.05 and sample size of 5, the critical value is 0.565, as you can see it here. For critical value of 0.565, we can say that our test statistic 0.26 here is less than or equal to the critical value. This means there is not enough evidence to reject the null hypothesis. This small size sample of 5 may as well come from a uniform distribution. Otherwise, if the critical value was less than this test statistic, then we would discover a huge amount of difference between the both CDFs, and we would say that there is enough statistical evidence to reject the null hypothesis, and this means we have proven the alternative hypothesis statistically, which is the fact that the sample does not conform to the uniformity property. So if you reject the null hypothesis, you are basically saying that the sample is not adapting the uniformity property. Now, one more thing here. In this example, we had a small sample size of 5, and the significance level was 0.05. Actually, for this small sample size, it should be better if we have used a greater significance level, such as 0.10. But in that case, at 0.10, the critical value will be 0.51, and still there wouldn't be enough evidence to reject the null hypothesis. So it does not matter. The result would be the same. However, as I have said, for small sample sizes, such as 5, it is better if you use a larger significance level, because otherwise the probability for the type 2 error is increasing very much. Remember, always start by indicating your null hypothesis and alternative hypothesis. Every statistical testing procedure starts with stating the null and alternative hypothesis. And in the end, you should not just say, we reject H0 or we do not reject H0. I mean, you need to give a solid conclusion. So what is the solid conclusion here? The sample may as well come from standard uniform distribution. Okay, you are giving conclusions to people who do not understand from H0 or rejecting or statistical testing. You are explaining situation to people who are curious if the sample is uniformly distributed or not. So you need to give them a solid conclusion about your testing procedure.